Hello everyone, welcome to the seminar today. Today, Joannes will tell from Umel University will tell us about the Cayley incidence graphs. Please.
Yeah. Hello everyone. Thanks for inviting me. So I will indeed talk about Cayley incidence graphs. And wait, I cannot. Okay. Yeah. So Evra, Feigon, Maurischat, and Parzanchevksi, they defined a class of biregular graphs, which they called Cayley bigraphs, and they are bipartite variants of Cayley graphs, and they use them to construct bipartite expanders. And in joint work with Soffía Árnadóttir, Alexey Gordeev, Sabrina Lato, and Tovohery Randrianarisoa, we gave an equivalent definition to the one that was given previously. And then we explored some of the basic properties of such graphs and some relations that they have to other combinatorial objects. We did opt for a different name to avoid confusion on the one hand with bi-Cayley graphs and also with Cayley digraphs. And today I will talk about the definition, of course, and then two classes of examples which are related to these Cayley incidence graphs. And then I will also talk about automorphisms of Cayley incidence graphs. So let's get into the definitions. So first I need to define a certain property, which we call the T axiom. So if we have a group G, and I will always denote the identity by E, unless for specific groups, or maybe I will write 0. If we have a set of or a collection of subsets of G containing the identity, then we say that this collection satisfies the T axiom if for all Ci and for any element G which is contained in this set Ci, it holds that G inverse times Ci is again an element of the collection pi. And the T in the name, it stands for translate. So translating any Ci by G inverse, where G is an element of, this should be G is an element of Ci. This gives another cell in pi in the collection that we are considering. And these sets Ci, we will call them cells. Because later on we will have a situation where you're close to a partition, so this name cell is kind of justified for this reason. And here we have a simple example. So let's say that we have the group Z, so the integers modulo 7. Then we can take 3 cells. So we can take, for example, 0, 1, 2, 0, 6, 5, and 0, 1, 6. And then we can verify that if we take, for example, this cell C1, so we see that the element 1 is inside of the cell. So translating by -1 should give another cell. And indeed, if we translate C1 by -1, then we get 0 minus 1, which is 6. We get 1 minus 1, which is 0, and we get 2 minus 1, which is 1. So we get that this translating C1 by -1 gives C3. And in fact, one can check that whatever one does, you can you have the situation. So these sets, they satisfy this T axiom. Another example is given here, that whenever we have a subgroup of H, then the collection containing only H also satisfies the T axiom. So this is, okay, if I have any element of my subgroup, G, so G is an element of H, then G inverse times H, it gives me the subgroup again. So this means that, this collection satisfies the T axiom. And more generally, any collection of subgroups, it satisfies the T axiom. And then we use this T axiom to define Cayley incidence graphs. So if we have a group G, and then we have a collection pi of cells which satisfies the T axiom, then we can define the Cayley incidence graph if there are two additional properties. So first of all, we assume that each cell has the same size k, so k is some integer, and any two distinct cells, they intersect only in the identity. So the reason that we take each cell to have size k is because we want because one wants the bipartite graph to be biregular, and then this ensures that this will be the case. So we have L cells, and each one has size k. Any two distinct cells intersect only in the identity, but they do intersect in the identity, and we have this T axiom. And then we can define the Cayley incidence graph to be a bipartite graph having two biparts, gamma and beta. So these are the two parts of the partition, where gamma consists of all of the elements in your group. So gamma is equal to G, and beta is equal to the set of all translates of possible cells. So beta is the collection of G times Ci, where Ci is an element of our original collection pi. And then the edges in this graph, they are given by, we put an edge between G and G times Ci for any G and any Ci. It should be noted, however, that these GCI, they are not uniquely represented. So it may be the case that G times Ci, it's the same set as H times Cj for some Gi, H, and J. So in this way, we can get edges of the form G to H times Cj, for example. But yeah, all edges are given in this form, G to G times Ci. There is an equivalent way to describe these edges. So another way to say it is that we have an edge between a G and G times Ci if and only if the element G is contained in this translated cell H times Cj. And just to kind of get used to these objects, we can look at the proof, which is more or less straightforward. So if we have, if we put an edge between G and G times Ci, well, because we assume that each cell Ci contains the identity, this means that G will be an element of G times Ci, because in particular, G times the identity is an element of G times Ci. And yeah, if we have some translate of some cells, so we have H times Cj, and if G is an element of H times Cj, then what we want to show is that H times Cj is equal to G times Cm for some m between 1 and L. And then we can, by assumption, we can write our G as H times Ga, where Ga is an element of Cj. And then by this T axiom, we know that Ga inverse times Cj is equal to some cell Cm. And then using this, one can write G times Cm as G times Ga inverse Cj, which, because G is equal to H times Ga, we see that G times Cm is the same as H times Ga inverse Cj, and this is thus H times Cj. And then, because we then wrote H times Cj as G times Cm, we see that we have an edge between G and H times Cj using the definition from the previous slide. So this definition already, or this property, it already points towards why we have this name incidence graph, but I will say more about this later. One also has a group action of G on the Cayley incidence graph, and it is given as follows. So on elements in gamma, so this is the bipart which is given by the group elements, it's simply multiplication on the left. So we just have that this vertex, if we want to apply G to it, then this is just G times H. For the elements in the other bipart in beta, we also just multiply this cell on the left, so we translate it by G. And this action is regular on the bipart gamma, but it's not necessarily regular on beta. So regular is free and transitive. And it can both fail to be free, or this is also called semi-regular, and it can also fail to be transitive. And later on in this talk, we will consider when it is regular. But now I think it's time for some examples. So here is our first example. So we have again the group Z modulo 7. And then we take some cells. We take C1 to be 0, 1, 5, C2 to be 0, 4, 6, and C3 to be 0, 2, 3. We can describe all of the translates of cells as follows. So we can all describe them as translates of C1. So C1 is 0, 1, 5. And then we have 1 plus C1, 2 plus C1, 3 plus C1, up to 6 plus C1. We see that 2 plus C1 is equal to C3. And we see that 6 plus C1 is equal to 0, 4, 6. And then here on the right, we have the actual graph. So we see that 0 is contained in the cells 0, 1, 5, 0, 2, 3, and 0, 4, 6. 1 is contained in 1, 2, 6, 1, 3, 4, and 0, 1, 0, 1, 5, and so on. So in this way, we get this bipartite graph. We see that the group elements are on the left, and we see that the cells are on the right. So this is an example of a Cayley incidence graph. And in fact, this gives you the incidence graph of the so-called Fano plane. This example, it fits into a general class of examples, which is the class of examples related to so-called NK1 difference sets. So just as to define it properly, we have the definition of a difference set here. So a subset of a group G is called an NK lambda difference set if the size of the set D is K, and if every non-identity group element can be written as a product D1 times D2 inverse, with D1 and D2 being elements of D in lambda ways. And this N in the definition is the size of the group. And whenever we have one of these NK1 difference sets, one can define a partition pi D, or not quite a partition because it will contain, or all of the cells will contain the identity, but one of these collections of cells, pi D. So the cells are given by D inverse times D, where D ranges through the difference sets. And then one needs to check that this collection satisfies the three properties which we need. So the T axiom, this is quite easy to see that it holds. So if we have an element in one of these cells, it's given by D inverse times D prime, which is an element of D inverse times D for some D. Then if we multiply this D inverse D by the inverse of this group element here, we see that we get the prime inverse D. So we get, again, a cell in the collection pi subscript D. All cells also have size K, and this is kind of clear by construction because all the cells are just translates of our set D. And then finally, the last property is a bit more tricky. So we need to check that two cells intersect in the identity if they are different from one another. And to show this, one basically needs to show that whenever we have two elements in two different cells, then they can be the same if and only if they are the identity. And these things, they are the identity if and only if A is equal to I and J is equal to B. J is equal to B. But we can rewrite this equation as dI inverse times dA is equal to dJ inverse times dB, to saying that dA times dB inverse is equal to di times dj inverse. And then we use the fact that D is a different set. So either this equation holds and they are the identity. If this equation holds and both sides are equal to the identity, then we see that A has to be equal to B and I has to be equal to J. But we assume that I is not equal to J, so that one cannot be the case. So this equation, it can only hold if these elements are non-identity. And since it's an NK1 difference set, there is only one way to write each group element as one of these products. So this means that A has to be equal to I and B has to be equal to J, which is precisely the thing that you have to show that this property holds. Yeah, and these partitions which you get in are not quite partitions, but these collections of cells, such that each non-identity, you get a partition such that each non-identity G appears in exactly one cell. So sorry for this kind of abuse of the word partition. Modulo up to the identity, each element is only contained in exactly one cell. And in fact, these different sets, they lead to, or they give you the NK1 designs with regular group actions on the points. And more generally, it is the case that when you have a Cayley incidence graph, such that each non-identity element G appears in exactly one cell, then this corresponds to NK1 designs with regular group action on the points. And using these different sets, one can construct incidence graph of affine planes and Desarguesian projective planes. And the Cayley incidence graph, they will then be the incidence graph of these planes. Another example that I wanted to talk about is that of incidence geometries or coset geometries. So there are certain coset geometries which you can also define using these Cayley incidence graphs. So a coset geometry, you can define it using subgroups H1 up to HL of a given group G. And then one can define an incidence graph of a coset geometry having vertices being the cosets of all of these subgroups. And then one puts an edge if the cosets belong to different subgroups, and if the intersection of these cosets considered as sets is non-empty. And if it is the case that HI intersection HJ is the identity for all of these groups, and if all of the subgroups have the same size K, then one can define a Cayley incidence graph by taking the collection H1 up to HL. This graph then has biparts given as in the definition of a Cayley incidence graph. So one part is given by G, and the other part is given by the union of all of these cosets. So we have the cosets of H1, we have the cosets of H2, we have the cosets of HL. And one puts an edge if the element G is contained in the coset. And this graph, this Cayley incidence graph, it's related to the incidence graph of the coset geometry, because the halved graph, this will give you the incidence graph of the coset geometry. So here I have a more concrete example, even though it is a bit simple. So we can take a group being the product of Z modulo 3 times Z modulo 3, and we can let H1 be the subgroup given by Z modulo 3 times 0, and then H2 is a subgroup given by 0 times Z modulo 3. And then the resulting graph, it will be a barycentric subdivision of K33. So the vertices in gamma, they will be the vertices that subdivide the edges, and the vertices of K33, they will be given by beta. And then the incidence graph of the coset geometry, this is precisely given by the complete bipartite graph K33. Yes, I think that's it for the examples that I wanted to talk about. So now I will kind of make something that I already mentioned in some sense more explicit. So to really say that these Cayley incidence graphs are incidence graphs, we need to talk about hypergraphs for a little bit. And a hypergraph, it's a generalization of a graph where you have a set V of vertices, and then you have a set E of subsets of V. And these subsets, they are called hyperedges. And I will denote these subsets by C1 up to Cm. So here we have a very simple example. We have 5 vertices. We have one hyperedge here, V1, V3. We have V0, V1 as a hyperedge, and we have V0, V2, V4 as a hyperedge. We will also talk about automorphisms of hypergraphs a bit later, and this is a map from the vertex set to the underlying vertex set, such that the image of a hyperedge is a such that phi of C is a hyperedge if and only if C is a hyperedge. And these automorphisms form a group, and a group action of a group G on a hypergraph H is then just a group homomorphism from G into the automorphism group of H. For hypergraphs, one can define the incidence graph as being the graph with vertex set V union E, and with edge sets, with edge set being the set of all incidences between vertices and edges. So you put an edge exactly when a vertex is contained in a hyperedge. And the incidence graph, this is a bipart graph with two biparts being V and E. And one can also recover the hypergraph if one is given the incidence graph and the partition into V and E. So we can briefly look at this example here. So on the left, we have the Fano plane, and you can consider it as a hypergraph having hyperedges being the lines. So we have the 0, 1, 5 being an hyperedge, 5 to 4, 1 to 6, and so on. And then we have the incidence graph here. And then the way that you recover the Fano plane as a hypergraph from the incidence graph is by looking at the vertices representing the hyperedges, and then you look at the neighbors to see which elements are contained in the hyperedge. So for the 0, 1, 5, we see that the neighbors are 0, 1, 5, and in this way we can recover that the hyperedge is given by 0, 1, 5. And then Cayley incidence graphs, they are incidence graph of certain hypergraphs. And more precisely, we can define this hypergraph here. So you put the vertex sets to be equal to G, and you put the set of hyperedges to be equal to G times Ci, where Ci are the cells in this collection, and G are group elements. These hypergraphs can be more generally called group hypergraphs, and we use this notation CH G pi for them. One has a group action where the group action is just given by left multiplication on the vertices. So here, this example, this is precisely the group hypergraph for this Cayley incidence graph showed before. There have been, we need some more terminology before we can state the precise relation between certain hypergraphs and these Cayley incidence graphs. So this is some hypergraph terminology. So a hypergraph is said to be uniform if every hyperedge has the same size K. It is said to be regular if every vertex is contained in L hyperedges, and it is said to be linear if every two hyperedges intersect in at most one vertex. And if you translate this into a statement about the incidence graph, we see that these statements, they are these properties, they are equivalent to the following properties. So the hypergraph is uniform if every vertex in the bipart beta, so this is the bipart which represents the hyperedges, has degree k. The hypergraph H is regular if every vertex which represents a vertex in the original hypergraph has degree L. And a hypergraph is linear if the girth is at least 6. And in fact, it turns out to be the case that, well, Cayley incidence graph, they precisely have these properties. So because each hyperedge is given by G times Ci for some G and some Ci, we see that the hypergraphs are uniform. We also see that they are regular because each vertex G is precisely contained in the hyperedges G times C1 up to G times CL, and they are also linear. This follows from this property that the intersection of two cells is equal to the identity if we take two distinct cells in the collection pi. It doesn't follow immediately, but after a short argument combined with this property, it follows. And there have been many suggestions to generalize definitions of Cayley graphs to hypergraphs throughout the years. And here I mentioned some references. So yeah, these are some references where people have generalized this Cayley graphs to hypergraphs in some ways. And one perspective that sometimes appears is that the variant of Sabi-Dussie's theorem should hold. So Sabi-Dussie's theorem, it says that a graph is a Cayley graph if and only if there is a group that acts regularly on the vertex set. And Yaisai and Lian Kwon, they proved variants of this theorem for hypergraph, stating that any hypergraph for which a group acts regularly on the vertex set, it must be given by a certain construction similar to this construction of a Cayley incidence graph. And based on this theorem, we gave a following characterization of the Cayley incidence graphs. So a graph gamma is isomorphic to a Cayley incidence graph if and only if there is a uniform, regular, and linear hypergraph H upon which the group G acts regularly, so it means it acts regularly on the vertex set, such that gamma is the incidence graph of H. So Cayley incidence graphs are precisely those that appear from regular and uniform and linear hypergraphs, which come with a regular group action on the vertex set. And here I have a sketch of a proof, but I think I will skip it so that I can talk about automorphisms. So for both Cayley graphs and bi-Cayley graphs, so first this was proven by Chris Gottsel in 1981, and then later by Zhao and Feng in 2016. For bi-Cayley graphs, the latter one. One can consider when a group automorphism of G induces a graph automorphism of the Cayley graph, bi-Cayley graph are now Cayley incidence graph. And it turns out that when you have a graph automorphism that comes from one of these group automorphisms, it's an automorphism which normalizes the action of the group G. And this normalizer, it's the set of all automorphisms of the graph. So they are graph automorphisms, such that for any G, there exists some other group element H, such that this phi composed with the left translation of G composed with phi inverse is given by L of H for the action where LG is the action of G on the vertex set. And yeah, so we will show that when we have these group automorphisms, they give rise to these graph automorphisms which normalize G. And to use this, we first consider the graph automorphisms which preserve the partition. And this is something that's general for bipartite graphs. Whenever you have an automorphism of a bipartite graph, either it switches the two parts. So if the biparts are given by gamma and b, either we have that phi of gamma is equal to gamma and phi of beta is equal to beta, or we have that phi of gamma is equal to beta and phi of beta is equal to gamma. And then in this way, we get a group homomorphism from the automorphism group of the bipartite graph to Z modulo 2. And we say that, I mean, the kernel of this morphism consists of all all graph automorphisms which fix the partition. So these are the ones with phi of gamma is equal to gamma and phi of beta is equal to beta. And the elements which are not in the kernel, they are precisely those graph automorphisms which swap the two sides of the bipartite graph. And so first we consider these that do not swap the sides. If we understand these that swap the sides, if we understand these that don't swap the sides, and if we then also can tell whether there exists some automorphism which swaps the side, then you can understand the entire automorphism group, because the automorphism group, it will be, yeah, it's then determined by these two things. Okay. So yeah, it's slightly easier to talk about these graph automorphisms as hypergraph automorphisms. So these automorphisms which don't swap the sides, they can be viewed as hypergraph automorphisms, since for any for any GCI which is in this bipart beta, the image is determined by the images of its neighbors. And then in this way, we can translate between these hypergraph automorphisms and the graph automorphisms which don't swap the sides. And these automorphisms, they are then given by a set map from G to G. And then there is a slightly standard argument which shows that an automorphism, it normalizes this action of G if it comes from a group automorphism. So we now show this. So, or rather, I mean, if also the phi of the identity is equal to the identity. So first you can reduce to this case that phi of the identity is equal to the identity, since one can always multiply on the left by some elements of G to make this the case, because elements of G, they are in particular contained inside of this normalizer. And then by definition, this is the condition for the automorphism phi to be in the normalizer. If we then apply this to the identity, we see that this H in this condition is given by phi of G. So we see that phi of G is equal to phi composed with L of G composed with phi inverse of E. Phi inverse of E, it's equal to E. So here we are left with L of G of E. So we have that phi of L of G, it should be equal to L of H applied in E. So this is just H. So we see that this relation here holds. And then by using this relation, we see that the left translation by phi of G times H, we can write it like this, and then we can rewrite it like this. And then we see that applying the relation again, that L, the left translation by phi of G of H, is the same as the left translation by phi of G, and then before the left translation by phi of g after the left translation by phi of h. And in this way, we see that these are group automorphisms. And because any edge containing the identity, it must again be an edge containing the identity. We see that for every ci, there must be some cj such that phi of ci is equal to cj. So hence these hypergraph automorphisms, they must come from these group automorphisms which permute pi. And then conversely, any such group automorphism which induces a permutation of pi, meaning that, yeah, for every ci, there is some cj such that phi of ci is equal to cj. This then also defines a hypergraph automorphisms. And this is really a quite straightforward computation now. So to show that this is the case, one simply sees that this phi of g times ci, it's phi of g times phi of ci, which is phi of g times cj. So if, yeah, this is then a hypergraph automorphism, since if g is inside of g times ci, then phi of g is inside of phi of g times cj. And by using this relation, which still holds, we see that it's also in this normalizer. And then this shows that we have determined those elements in the normalizer that that don't swap these parts. So they're in the kernel of this sigma. It's not entirely immediate, but you basically get it from these two facts, that this normalizer intersected with the kernel of this sigma, so those group elements in the normalizer that don't swap the parts, they are given by a semi-direct product of the automorphisms, the group automorphisms that permute this pi with g. Okay. And now we want to move on to the automorphisms which swap the two sides. And here we need to say a bit more about the structure of these graphs before we can really state a theorem. So we need to talk a bit about first the dual hypergraph, and then we also need to talk about when the action of G is regular on beta. So for any hypergraph H, one can define a dual hypergraph, which is, it has the same incidence graph, but one basically swaps the roles of the vertex sets and the edge sets. So this dual hypergraph H star, it has vertex set E, and it has edge set E star. So the vertices of H star, they are the edges of our original hypergraph, and the edges are given by collections of hyperedges, so collections of elements of E, and they are precisely the collections of elements of E such that V is contained in Ci. And really, it's much easier to think of this as, yeah, swapping the roles of gamma and beta in this bipartite graph, and then constructing this this hypergraph. And to have a automorphism which swaps the two sides for this hypergraph, we need to understand when the dual hypergraph can also be the hypergraph for a Cayley incidence graph. And one thing which we need for sure is that we need the action to be regular on the hyperedges, because the hyperedges will be the vertices of our the dual hypergraph. So this means that by this Sabidussi type result, that, yeah, we need the action to be regular. So when is the action regular? Well, okay, first we need to look at when the action is free or semi-regular. And it turns out to be the case that the action is regular if for any cell Ci, we don't have that both G is an element of Ci and G inverse is an element of Ci. So the stabilizer of any of these cells Ci is the collection of elements G such that both G is an element of Ci and G inverse is an element of Ci. So here I give a short proof of this fact, which I will skip. But the conclusion of this reasoning is that the stabilizer is given by the element such that, so the stabilizer of Ci is given by the elements in G such that both G is an element of Ci and G inverse is an element of Ci. And then for other cells, we can also determine the stabilizer just by generalities on group actions. Then it's given by the the conjugate subgroup of the stabilizer of Ci. So if all of the stabilizers of Ci are trivial, this means that these conjugated subgroups also have to be trivial. So we see that the action is free if and only if at most one of G and G inverse is an element of Ci for all cells Ci. And then we also want to consider when it's transitive. Well, it then suffices to check that for any of the two cells in the partition, there exists some element Gi such that Gi times C1 is equal to Ci. And yeah, this is the case because all other hyperedges are given by G times Ci for some cell Ci and some group element G. So then if we can force this to be the case, that there exists some Gi such that Gi times C1 is equal to Ci, then this means that the action of the group is transitive. And this is the case if the cells C2 up to Cl are given by G2 times C1, G2 inverse times C1 up to GL inverse times C1 for some group elements G2 up to GL, which are contained also in this cell C1. And this means that if the action is regular, it determines the cells C1 up to CL. So the cells are then given by this first cell, which is given by E, G2 up to GK. The second cell is then given by G2 inverse times C1, so it's G2 inverse E, G2 inverse times G3, and so on. And then the final cell, it's GK inverse times C1. And in particular, if the action is regular, it also forces K to be equal to L. If the action of G on these cells is regular, it actually turns out that the hypergraph dual will also be a group hypergraph associated to a Cayley incidence graph. And to understand the edges in the dual graph, well, they are collections of edges containing a single group element, let's say H. So hyperedges in the dual graph, they're given by these collections H times C1 up to H times CL, since these are all the edges which contain H. And in particular, C1 up to CL is such a hyperedge in H star. If we then treat C1 as being the identity in this new Cayley incidence graph, or the hypergraph associated to the new Cayley incidence graph, we see that, since Ci is given by Gi inverse times C1, that one of the cells should be given by E G2 inverse up to GK inverse. And then we can define the other cells using this E G2 inverse up to GK inverse. And this leads to precisely the hypergraph that we want. So this is the kind of the conclusion of this digression on the dual graphs and the regular actions. So if the action is regular on the edges, then the cells are given by G2 up to GK, G2 inverse times C1 up to GK inverse times C1. And then the dual graph of this group hypergraph, it has these cells. So the first cell is G2 inverse up to GK inverse. The second cell is G2 times C1 inverse, because you're constructing it in the same way as you do for the C1 up to CL, since we know that the action has to be regular on these hyperedges. And then, yeah, CL is also, for all of these cells, it's given by a cell CI star, it's GI times C1 star. And now we are ready to return to our study of the graph automorphisms. So, okay, this is kind of a reminder of what I said earlier. So it suffices to understand when there is a single graph automorphism with which swaps the sides to see if to consider the group of all these automorphisms, because if this group homomorphism sigma has some element which maps to 1, then it means that the automorphism group, it's a 2 extension of the kernel of sigma. And then from what we saw for the hypergraph, it seems likely that there exists such a graph automorphism in the normalizer of this G, if there is a group automorphism from G to G such that phi of C1 is equal to Ci star. And this turns out to be the case. And now I will show the one direction, which shows that, okay, if we have such a group automorphism, then we get a graph automorphism. So what we want to show is that we have a group, so we assume that we have a group automorphism phi such that phi of C1 is Ci star for some I. And then if we consider C1 and C1 star as sets of group elements, we know that there is some group element G phi such that phi of C1 is equal to G phi C1 star. And then we can use this group element to define a automorphism of the Cayley incidence graph. On elements in gamma, it's defined by taking G to phi of G times C1. In elements in beta, they are given by G times C1 for some G. It's defined by taking G of C1 to phi of G times G phi. And we have that an element H is contained in G of C1 if and only if phi of G inverse H is an element of phi of C1. So this is, by applying this automorphism phi to this condition here that H is an element of G times C1. And then we can rewrite this to this form. So we can rewrite it to saying that G phi inverse times phi of G inverse of times H is an element of C1 star. And then by taking inverses, we get this relation. So we get that phi of H inverse times G phi is an element of C1. And this is then equivalent to saying that phi of G times G phi is an element of phi of H times C1. So we see that this H is an element of G times C1, if and only if phi of G times G phi is an element of phi of H times C1. But looking at our definition of the graph automorphism phi, this is precisely, this ensures that our, this condition here, it ensures that our graph automorphism is well defined. And since we have this commuting relation between the action of G and this f of phi, we also see that it must be in the normalizer. And then we can basically sum up. So we have determined this normalizer of G inside of the automorphism group of a Cayley incidence graph. So if there is a group automorphism such that phi of C1 is equal to Cj star for some j, then we see that the normalizer of G, it's automorphic to this group. So it's first this semi-direct product of these automorphisms of G preserving the partition and G, and then this other automorphism phi with this special property. If there is no such group automorphism, then we are simply left with this part. And so this, this group here, this group generated by the semi-direct product and phi, it's actually a 2 extension of this semi-direct product. So it has this as a order, as an index 2 subgroup. And then because I don't think I have time, I will skip the examples. But the examples are actually 2 examples of these Cayley incidence graphs where you can swap the sites. So actually for any abelian group, you can take some automorphism, and also for the quaternion group, you can find some example where you swap the sites. Okay, thank you all for listening, and that was it. Yeah.
Thank you, Joannes. Any questions? Are there some conditions for a Cayley incidence graph to be a Cayley graph?
So we have some actually. So I mean, for a Cayley incidence graph that you have to be in this case where the action on wait, let me not say yeah, we have some results on this. So actually, if we have one of these automorphisms which swaps the sides,
yeah.
This means that it will be a Cayley graph.
Oh.
I think that my co-authors are also in the audience. So if I say something stupid, they should stop me.
I think, didn't we show that if we have an abelian group and we have a regular Cayley incidence graph, it must be a Cayley graph?
Yes, I think that it follows from these 2 things somehow. That we have this example, and then we have this theorem. So yeah, in particular, when the action is regular for an abelian group, then it's a Cayley graph.
Yeah. So basically, what happens is that you get the Cayley incidence graph for an abelian group is going to be the Cayley graph for the generalized dihedral group.
Mm.
Yeah.
Thank you. Any other questions? You didn't talk about it, but are there, I'm just curious, are there some nice way to calculate the eigenvalues? So what's a Cayley incidence graph?
So they are given by you can calculate the spectrum of the Cayley incidence graph based on the spectrum of the Cayley graph. So yeah, we can get the spectrum for the Cayley incidence graphs from the spectrum of the Cayley graphs. So sorry, there is something I didn't define. So if you take a Cayley graph, if you have a Cayley incidence graph, so we have a bunch of cells, C1 up to like here we have C1 up to C3. We can take the union of all of the group elements in these cells, and then we get some set S. And then if we take away the identity from this set, so here it would be 1, 5, 4, 6, 2, 3. If we look at this set and then we look at the Cayley graph for this set S, then we can get the spectrum of the Cayley incidence graph based on the spectrum of the Cayley graph.
So for each Cayley incidence graph, you can define the related Cayley graph. Then you can get the eigenvalues.
So in general, we just take the union of all the cells and then we take away the identity. And then you get the Cayley graph. And this allows you to compute a spectrum.
Thank you.